Okay, so we're going to take the idea that we talked about already with area and those representative rectangles and start spinning all kinds of areas and making three-dimensional figures. This will be fun. It's still a very algorithmic approach, but it can be kind of confusing because we'll end up with 3 different techniques and you need to know all 3 different techniques. Today we're going to do 2 of them. The first 2 fall under the category of being the disk method, which we'll get to in a second. So we're going to talk about the disk method, then a variation of the disk method is something called the washer method, but most importantly today you should be sure to give at least 2 hugs today. Anybody already done? Good, excellent. Is that 2? Yeah. You're good? Okay, thank you. Did you just give Vinny 2 hugs, or did you?
TJ and Vinny.
Okay, well done. Excellent. So you're done with that part of the.
Well.
I understand. Okay, I'm going to go slow and make sure that you understand this. This is not, in my opinion, not something you just memorize. There is a formula here, but the formula won't make much sense if you don't understand what's going on. All right, so don't freak out yet. Here's our representative rectangle, and we're just changing a little bit of notation here because we're going to call it W because we're still playing with a rectangle that we can actually see. If I take that rectangle and I spin it around this line, which is called the axis of revolution, I generate one of those. You are not going to be expected to draw these 3-dimensional figures. If you can, good job. No bonus points for you. You do need to draw the 2-dimensional figures though. All right, so we're going to take a rectangle. When we spin that rectangle, we get this thing which we call a disk. You may see it as a cylinder on its side, a short cylinder on its side, but we're going to call it a disk. The width of the rectangle is the height of the disk. R is the radius of the disk, also known as the height of our original rectangle. So those representative rectangles that we used in the last section become very relevant here. Okay. The volume of that puppy is pi r squared W. That's the same thing that you learned in geometry for the volume of a cylinder. We just changed some of the notation. Instead of little r, we used a capital R. Instead of a height, we used a W because that's the width of our rectangle. Okay so far? Yeah, good. So we did that already. Area of the disk times the width of the disk. The area of that disk is a circle, so notice this pi r squared is just the area of the circle, and then the width is how many of those you got stat, or how wide is that thingamajobber. We're going to take that idea and calculate the volume of solids. So if you can see in this picture, if you can see in this picture, I've got a function that looks something like that. I want to find the volume that I generate when I take that function and I spin it around the x-axis. In simplistic terms, what we're going to do is take one little rectangle, in this case I have it colored in yellow, spin that around and create a disk, which is what this looks like over here. There's my disk. And then if I do that for a bunch of disks, I end up with something that resembles the shape that I'd get when I spin that puppy around the x-axis. Is that concept okay so far? Okay, good. It would be nice if it stayed that easy. It's not going to, but like I said, we'll go slow and try to make sense of this. The first picture on the right obviously is not going to be good enough for us. We got corners there. It doesn't look anything like what we want it to look like, which is what this guy gives us, this nice smooth curve, if we started with a function like over here on the left. So the question is, how do we get a more accurate answer? How do I take this big, scary, squared off looking ugliness and turn it into something nice and smooth?
Smaller W's.
I'm sorry?
Smaller W's.
Or?
More rectangles.
Same thing. Smaller W's or more rectangles. And those two are related to each other. If I shrink W, then the number of rectangles will go up. If I increase the number of rectangles, W would get smaller. How small do we want W to be? Which we would refer to it using what notation? dx. Okay. We're going to use the second one. It's easier. So again, delta x or W from the previous picture will become dx. We want really, really, really skinny rectangles. So if I've got really skinny rectangles and I put them all together and add all those up, I'll get the volume of that shape. How do I add things up? Integrals, right, because remember I keep using the term accumulator. The integral is an accumulator, so it's going to add all those things up. So, simplistically stated, we take a rectangle, we spin it, we get a disk. We use the integral to add up all those disks, we're done, we got a volume. Easy? Good, let's try it. For those of you that are visual learners, I've got some doohickeys here that'll help you see what's going on. If this runs, yes it is. Okay, good. So up here, I've got a rectangle. You'll see it's supposed to be a rectangle. It started to spin already. A couple things to notice about that rectangle. Number one, it's touching the axis of revolution. That's really important. And number two, it's perpendicular to the axis of revolution. So when you spin it, you get that disk. And that's how it creates the disk. Okay, nothing fancy there. Now what's that going to do for us? Well, if we take that and we get something like this guy, reset that. This is how we're going to apply it. So I took a function here. I'm using the square root of x as my representation. And I've got a rectangle in there. If I spin that rectangle, again, for the third or fourth time, you see that disk that it generates. So if I then split up into a whole bunch of rectangles and spin them, you see that I get the figure. It's a little hard to see there, but you get the idea. And if I increase the number of rectangles, I get closer and closer to that smooth figure. I don't know if you can see from back there, but you see all these little jagged edges there. Those are all the corners of the rectangles. If I change the number of rectangles, it would then smooth out. If I make this, let's see, 100. Make that go away and do it again. You see it smooths out. Okay. And as that number increases, it'll get smoother and smoother. So if we want the most accurate answer, we want that number to go to infinity. That's not it. That's not it. Okay. So there it is. Again, if you take those infinite number, you end up with that shape. You get that thingamajobber. That one's a little different, and we'll actually come back to this. Notice that this one is not revolving around the x-axis, so the rectangle is not touching the axis of revolution. We'll come to that later. Okay? So quit this. Don't save. All right, so let's do the first example. It'll make a little bit more sense on the first example. In my opinion, the hardest thing in these types of problems, in the disk method problems, is drawing the picture. So I'm not going to show you a picture. I'm going to let you draw that on your own. Figure out what that sketch looks like and try to somewhat accurately draw a representation of the area being defined by those functions. And I'll talk while you're doing that. What's the graph of x squared plus 3 look like? Sorry? Yep, parabola moved up 3. What's x equals negative 2 look like? Beautiful. And x equals 2? And what's the x-axis look like? The x-axis. Okay. Excellent axes, my friend. Thank you. Some of the best I've seen. Snapping that pencil like you've been working out too.
Yeah.
I can see. Breaking that pencil lead like crazy. Hopefully you sketch something that looks like this yellow region. You don't have to draw the three-dimensional figure if you want to. I mean, this is America, knock yourself out. But in this picture, not only do I have the region that we're talking about, but I also drew in a representative rectangle. You will also need to draw in a representative rectangle somewhere. I don't care where, but just somewhere in that region. Okay, we good? Now, let's find the volume of that thing. So I need to find the area of the rectangle first. How do I find the area of the rectangle? How's it good?
Base rectangle.
Correct. And what's the height?
X squared plus 3. Yeah, and then times dx.
Good. Is that it?
Take the integral
From?
I always get confused where like the boundary should be. 7.
To answer that question, you want to ask yourself, where am I taking rectangles? From where to where? I'm taking rectangles from -2 all the way over to 2. And that'll define your limits of integration.
Always.
I hesitate to use always, but
Yeah.
a majority of the time, yes.
Okay.
Okay, so Allie told us the area of that rectangle is x squared plus 3 times dx. I want to be clear though, that's x squared plus 3 minus 0. Top minus bottom still applies, but the bottom here is the x-axis, which has a value of 0. X squared plus 3 minus 0. The width of that rectangle is dx because we want it to be really skinny. How do you find the volume of the disk then? In that picture, what's capital R? What's the radius of the disk we're going to create by spinning that blue rectangle? Yeah, the height. Notice the height of the rectangle is the same as the radius of the disk. So then the volume of the disk becomes that. Radius squared times pi times dx. So that's one disk, and that's the hard part. If you can get that, the rest of it is easy. Because as Allie said, then we want to look at all the disks from -2 to 2. And we get that. I always move the pi out in front because it's constant. Celeste, you got a question?
Yeah, can you go over what the volume equation again, where it came from?
Yeah, it's, see that little disk in there?
Mm-hmm.
The volume of that disk, if you think of it as a cylinder on its side, it's the area of the circle times the width. So the height of that cylinder is actually, when you turn it sideways, the dx that we're looking for. That doesn't help, does it? Okay. Then we'll draw a picture. That's what I'm finding the volume of, right?
Mm-hmm.
Which is a cylinder. The area of a cylinder is pi r squared times h.
Yes.
For our purposes, however, the little r is actually capital R, and h is actually dx. So we're taking that cylinder and turning it 90 degrees so that it's up and down.
Okay.
So in this picture, there's the height of the cylinder, there's the radius, and when you spin that, you get that. That's that formula, pi capital R squared times dx.
Okay.
Okay?
That helps me.
Good. Are we okay with this? Yeah, Peyton.
So you're always just gonna plug the function in for r, and then dx for the height, not always, but most of the time.
Right, because it'll change in a couple minutes.
Okay.
Yeah. Because we're going to add some more complicated things to it to make it a little more interesting. Yeah.
Why do you have to take the integral?
Because this thing here represents the volume of only this blue disk. And I want to add up all the infinite number of disks that we have, and that's what the integral does, because again, remember the integral is an accumulator.
Yeah.
Okay. Anything else before we move on? I was too lazy to do the calculation by hand, so I FN inted that. Don't get in the habit of FN inting too much. How would you take the integral of that function? No chain rule in integrals. No U substitution doesn't work here. Good guess though.
Simplify for this, split everything. And
Yeah, multiply that puppy out. X to the fourth.
Kendrick.
Yes. X to the fourth plus 6x squared plus 9. Take the integral of each of those parts, plug in 2, plug in -2. Done. Good. So, how to make things more interesting? Well, instead of just spinning around the x-axis, let's spin it around the y-axis. If you spin it around the y-axis, it's the exact same thing, except x's become y's and y's become x's. dx's become dy's, etc., etc. So here it is in terms of x's. We just did that. Here it is in terms of y. Nothing fancy happens. It just changes things a little bit. X's become y's. But again, the two important things that you have to realize is that even when we're working in terms of y, our rectangle is touching the axis of revolution, and it's still perpendicular to the axis of revolution. You have to be able to recognize that, because when one of those things isn't satisfied, we have to use a different method. Okay, so for disks, again, perpendicular to the axis of revolution, touching the axis of revolution. Next example. Again, I'll let you draw that, and then we'll solve it together. Does anybody have any idea what x to the fifth looks like?
It's got 4 bones.
I'm sorry, what?
It's supposed to have like 4 bones. Oh.
Anybody else?
Steep x to the third.
It's a steep x to the third, correct. And your graph doesn't have to be 100% accurate, so it's not like you need to plot every single point, but you should have a general idea of what it looks like. What's the line y equals 1 look like?
Horizontal.
1. 32. There's the region we're going to spin. When you're doing your diagrams, also show the axis of revolution by drawing the little circle there, so you can see, or you can demonstrate which axis you're revolving around. I'm having trouble with the English language today. I'm going to switch to German. Representative rectangle. Seems like a silly question, but is that rectangle horizontal or vertical? If the rectangle is horizontal, do I work with x's or y's? Y. So this puppy's going to be in terms of y. This will be fun. Since it's going to be in terms of y, I need to solve this. So x is equal to y to the 1/5 power. That wasn't that difficult. Is the rectangle touching the axis of revolution? Yes. Is it perpendicular to the axis of revolution? Yes. Good. What's r? There it is graphically. But what's the expression for the height of that rectangle?
Y to the y.
I'm sorry?
Y to the 1/5.
Correct. When we're first learning this, however, you might want to do it as y to the 1/5 minus 0. Because right minus left still applies. It seems silly because we know that y to the 1/5 minus 0 is y to the 1/5. But when the problems get more complicated, that'll become pretty important. Okay, so what's the volume of one disk? Pi times
Y to the 1/5.
y to the 1/5. No. Squared, good. Pi r squared times dx. Good.
dy.
Right, that's what I meant. Good job. Just seeing who's paying attention. You guys passed with flying colors. Proud of you. Anybody bought that? Okay, thanks. Thank you, Kendrick. You're either very supportive or not so sharp. We'll go with supportive. Excellent. Okay, now what? Why?
So you can accumulate all of this.
Yeah, well said. Don't forget your notation. We've done area, now we're doing volume. You need to designate that you know what you're talking about. Pi times the integral from what to what?
1
To 32.
Excellent. 1 to 32. So, Allie, I think it was you I was talking about. Again, the question is, where am I sliding rectangles from what to what?
Yeah.
From 1 up to 32. Of this mess. Y to the 2/5 dy. I got the dy right this time.
That's good.
Easy peasy, right? You could FN int it, you could do it by hand. This one you should probably do by hand. Plug in 32, plug in 1, solve. Which we're not going to do now because we don't really care about the answer, we care about the method more than the answer. So that's what we had. Which, in case you were playing along at the home game, 284.987. When you start doing these kind of problems, questions like, well, does that make any sense, kind of get thrown out the window, because I have no idea if that's a reasonable volume for that funky shape if you spin it around the y-axis. So just look for obvious things, like if you get 0, that's probably wrong. If you get negative, you probably did something wrong. So, unless it's something really bizarre, you're not going to be able to use that to check. Okay. How are we doing so far before we move on to this?
Good.
We're good? All right, let's take a quick intermission, grab a cookie and a Capri Sun, and then we'll start in about 2 minutes. Go. One at a time, please. Just, okay. Left isn't bashful. Yes, sir. Limits packet? Yep.
How bad is
A little bit of both.
So do you want me to release it out of the bathroom? I left it in
Yeah, that's April.
We gotta drink choice.
Sorry?
Oh.
Before you and nothing yeah, I'll catch him. He'll get all worked up like JoJo the Circus Boy. I'll go boogie. I'm gonna try to talk without spitting cookie all over everybody. Good thing you wore a white shirt today, Kevin.
Oh, Miller.
Alrighty. So the washer method. The two questions I said that were important. Is the rectangle perpendicular to the axis of revolution, and does it touch, becomes relevant here with the washer method. For the washer method, you're still going to be perpendicular to the axis of revolution, but what happens if it's not touching the axis? So here's my little rectangle floating up above the axis of revolution. When you spin it, you get this guy, which is a little hard to see because it's yellow, but that's called a washer. It's a disc with a hole punched through it. There are two distances we're concerned about in this picture. One is capital R and one is lowercase r, which I call big radius and little radius. It can get a little confusing in pictures. So what you want to remember is that big radius, you might want to write this down by the way, big radius is the furthest distance from the axis of revolution to the rectangle. Little radius is the closest distance from the axis of revolution to the rectangle. So if you look up here in this picture, you can see the closest distance there is that little r, which is labeled lowercase r, and then big radius is the farthest distance. To find the volume of that washer, you calculate the volume of the whole disc and you calculate the volume of the hole and subtract them. When you clean it up a little bit, you get to this formula here, which I believe is on the next slide. It is not anywhere near the next slide. Hold on a second. I guess you got to write that one down then. pi times parentheses capital R squared minus little r squared all times w. But again, w for us is what? Dx, correct. We want w to be really, really skinny. Okay, so we take this little shape here, which is like maybe a parabola intersected with a line, and we spin it around the axis of revolution, and that little widget turns into the cone of shame. Anybody?
Yeah, I got it.
Okay, just want to make sure you're with me. Here's another example. Taking this area that's floating out in the middle of nowhere, you spin it and you get that funky shape in red. And then the far one to the far right just shows you what one of those washers look like. And you don't have to draw the three-dimensional pictures, you're just going to have to draw the two-dimensional pictures. Okay, so let's go back to that sketch I had before and show you what generates the washers. Yes, I know about my computer. Okay, so now we take this guy and we pull it off the axis and get rid of that mess there. Come on. And revolve. And now we get that washer. And you can see from the picture that this is our big radius and that's the little radius. So how far is the rectangle away from it and how close is the rectangle to the axis of revolution? So I said there's three methods. That the disc method is the first way, the washer is the second way, and then I'll give you a preview. What we're going to do in section 7.3 is what's called shells, where now your rectangle is parallel to the axis of revolution, and you end up with something like that. That'll be fun. We'll save that for later. And then if you take that idea and where is it? There it is. Reset that and then revolve. So then you spin that whole thing around. Because again, your rectangle is not touching the axis of revolution. You generate a shape with a hole in the middle. And we're going to calculate the volume of these bad boys. That's, don't save, come back to here. So there's the general formula. Common mistake that people make here. Notice it's capital R squared minus little r squared. Not capital R minus little r quantity squared. You're squaring the individual parts. Still a pi sitting out in front of it because you're still finding the area of a circle. These problems can be made considerably easier if you draw a careful sketch. If you label everything clearly, you'll be okay. So maybe you want to do it on graph paper, maybe you want to, I don't know, just a suggestion. Or maybe you just want to quit and give up.
Wait, can you stay for a second? Yeah, that's more like a second. Yeah, we're good. Thanks.
We've seen this shape before. That's the square root of x intersected with the function x squared. Spin that, and we get this guy. I don't even know what you'd call that. So we're going to do this problem. Outer radius would be that farthest distance. So what's the farthest distance? In this case, it's the top from the rectangle. The inner radius is the closest point, which in this case is the squared function. And when you put that all together, we get capital R squared. Just for giggles, what's the square root of x squared?
X.
Good. And what's x squared squared?
X fourth.
X to the fourth. Good. And we get that. Why 0 to 1? Because in the picture, 0 to 1 told us where we're taking rectangles from. Those are the points of intersection which determine the bounded area. Too fast? I actually worked this one out just for giggles. 3 pi over 10. Did it by hand. You should be able to do it by hand also. Don't rely on the FN in too much. Especially on the quiz tomorrow, I will require that you show the antiderivative. You could use FN in to check, but you still got to show all the work. Okie doke. Let's do one from scratch. By look, oh no, we're gonna save that one for later. All right, let's do this then. Okay, so we started with the disk method. Then we complicated it by taking the disk off the axis of revolution to get a washer. How else can we make it more complicated? Let's spin it around something other than the x-axis or the y-axis. This will be fun. So instead of spinning it around the x-axis where the value is 0, now all of a sudden we're spinning it around a value that's something different than 0, and we have to take that into account. Still going to use top minus bottom and right minus left. Those rules hold true for everything that we do with these volume revolution problems. So let's look at it in this example. While I'm talking, draw what you think will be the region that we're talking about here, defined by y equals x squared plus 2. What's that look like, by the way?
Facing upwards, moved up to.
Thank you. Well said. What's y equals 1/2 x plus 1 look like? Line. Did you poke yourself in the eye with a straw?
I flung juice my eye. It happens.
That could possibly be the first and only Capri Sun injury I've ever witnessed. Other than, obviously, poking yourself with the straw. Are you okay?
I'm good.
Is it burning or no?
Sudden reaction.
Not something you would recommend though?
No.
Okay. What's the line x equals 0 look like? Was that you?
I thought it was.
That was the straw.
It sounded like a little squeal of delight because I asked what x equals 0 looks like.
I'll try to remake it. Nope. I swear it came from the straw.
They all said.
It's okay. Any luck drawing the picture?
No, I think it's
No? No? Perfect. Well done. You got nothing. What do you got? Half of it. What do you got? You're almost there. Uh-huh. See how small that is, they probably want. Yeah, but that's okay. Beats juice in the eye.
Where's the region we're gonna work with?
Okay. Remember, it's gotta be a bounded region, meaning it's gotta be completely contained, otherwise the answer is infinity. And we won't get to those. So you should get something like that. Whoa. That's better. And the region we're looking for is this guy. Because that's the bounded region. All the other spaces on there are not bounded, they're infinite. Representative rectangle. Right there. And just so we're all clear on the problem, the axis of revolution is the line y equals 3, which is that guy up on top. How are we doing so far? Hey.
When you do top minus bottom now, with the top, if you're spinning it around the x-axis, would it be blue line?
Can we wait a second on that question? Okay. Come here, Tommy. I'm not gonna hurt you. go to the diagram and draw in or mark off where capital R is
Capital R.
using the representative rectangle.
Okay.
Guys are idiots.
Um,
Sorry to put you on the spot, but it's good for you. It builds character.
okay.
Yep, put your hair in your chest.
It's gonna be vertical or horizontal.
You tell me. Hold on, while you think about it, I'll ask for some help from the crowd. How do we define capital R? Farthest distance of the representative rectangle from the axis of revolution. There's a lot of fancy words in that statement.
Farthest distance from the.
Farthest distance from the axis of revolution to a point on the representative rectangle. Where's the axis of revolution?
Right there.
Good. Where's my representative rectangle?
Right here.
Good. So what's the farthest distance from the green to the red?
Right.
Nope.
Right here.
Yep.
Okay.
Okay. You want to mark that somehow? Maybe draw a brace. How are your braces? Or a bracket?
Oh. Like from here to here?
Yeah.
Oh, okay.
Oh, well done on the brace. Most people aren't very good at it.
I don't know how to.
Yeah, I'm a bracket.
Well done. Anna? All right, come on up.
Oh, no, I had a question, but.
Oh.
I didn't answer
I didn't say anything.
it. I saw it on the board.
Oh, okay. Now come up. And don't look at me in that tone of voice. Draw little r. Well done. Okay, thank you. Can you all do that? That's crucial to making your life a lot easier. If you can identify capital R and R in your well-drawn picture, the volume is pretty trivial. I'm coming back to your question, Peyton. Hold on. Okay, now the big one. How long is capital R? Before you answer that question, let me ask you this question. If this is at 5 and this is at 3, how far is that distance? Why?
5 minus 5 minus 3.
Okay, so what's the distance for capital R?
Minus half x plus 1.
Wait, we're all talking at the same time. Okay, then nobody talks.
You want the entire distance of capital
I want the length of R. And it will not, I'll give you a hint, it's not a numerical value.
3 minus 1/2 x plus 1.
Bingo. Well done. Everybody get that? Nope, they're confused. So remember when I said top minus bottom and right minus left still applies? That's what we're doing here. Top minus bottom. What's on the top? Excuse me. What's on the top? 3. What's on the bottom? The blue, which is 1/2 x plus 1. So capital R is 3 minus the quantity, importante parentheses, 1/2 x plus 1. Okay. Okay, boss. What's little r?
3 minus 3x squared plus 2.
Bingo. 3 minus quantity. Nicely done on the quantity. X squared plus 2. Yes?
Oh no.
Oh. You were literally clearing your throat, not trying to get my attention.
Yeah.
I understand. Okay. Now what?
Square them
Why?
and then subtract them.
Why?
Find the value.
Of?
This washer.
Good. Let's find the volume of one washer. Well, can you jump right into the integral? Are we okay? Can everybody handle that, or should we take it in steps? Integral. Okay, so the volume of, there's a pi sitting out in front. Celeste, what are we going from? From what to what?
Oh gosh. 0 to 1.
0 to 1 of
R squared.
Good. Capital R squared, which is 3 minus the quantity, 1/2 x plus 1, close parentheses, that whole mess squared. Minus what?
Parentheses.
Uh-huh.
3 minus parentheses.
Uh-huh.
X squared plus 2 parentheses squared parentheses
Now, just to keep things
or bracket.
above board, I'm going to switch to a bracket because this whole mess has got to be in a bracket with a dx. You have to have that differential associated with your integral. Especially now because it has an actual physical representation in the problem itself. It's not just there in the other problems where we were learning how to take the integral of x squared dx, where you're just there to say, oh yeah, the variable's x. Now it has a real important component to the problem in that it represents a physical distance. We are not going to solve that mess. How would you solve this mess, Kendrick?
Multiply it out.
You would multiply it out, correct. That's one possibility. How else could you solve it? You could f(n) int it. That's 2. Third possibility?
Check the back of the book.
You could check the back of the book. Excellent. Fourth possibility.
Give up.
Ask me. Give up. Cry. Cheat. What am I forgetting?
Don't do it.
Don't do it. Which, like a subset of giving up. Right. Anything else? You could also, yes, Paige?
I have a question.
Okay, hold on, let me finish my
Split
ninth
it.
possibility. What?
Split it.
Split it into 2 separate integrals. Yeah, what do you got?
Why'd you do the 3 minus the function?
Where these come from?
Yes.
Top minus bottom. Okay?
Are you spinning it around the x-axis?
No, I'm spinning it around that axis.
Then why did you do 3 minus?
Because.
Don't overcomplicate it, just remember top minus bottom. So you're getting confused because of how we had it set up before where the axis was always below the rectangle and then it spun this way. Now we're switching it, so now it's going to spin. I can't do that. It's going to spin a different way. So instead of complicating it by worrying about, well, it's above and it's going to go down or it's below and it's going to come up, just remember top minus bottom. So if I take that axis of revolution and I move it down to -2, now my top is different.
So it'd be -2 minus.
No, it'd be the other way around. It'd be the function minus, because again, it's top, the function up on top, minus -2.
Okay.
Okay? And if we spin it in terms of y, then we'll start talking right minus left, which we'll deal with later. Okay? How bad do you think this is going to be? It's actually not too bad. If you can draw a good picture, if you can identify R, capital R and little r, and you remember top minus bottom and right minus left, you'll be okay. So that's what we had before. That's top minus bottom for the capital R, the big radius. There's a little radius, and we are done. Do you guys even know what this is?
Floppy disk.
It's a floppy disk, yeah.
Saves them.
Yeah, and that's a washer.
Yeah. So just
Disk and washer.
I think it's a GE. In case you really care. Have you guys ever seen the other discs, a floppy disk? The bigger ones? No? You have no idea what I'm talking about, do you? Never mind.
I got you.
Okay, so tomorrow we have a quiz over just area. Make sure that you can set up your integrals correctly and do them by hand. Even though it is a calculator quiz, I'm still going to require that you do the antiderivatives and set everything up clearly. On Wednesday, no, that's tomorrow's Wednesday. On Thursday, when we come back, we will take a look at a couple of the problems from yesterday and take a look at this day 106 stuff. The quiz tomorrow will not take all periods, so we'll have some time at the beginning of the period to answer some of the questions of the homework that was due today, the rest of the 7-1 homework. And then I'll collect both of those 7-1 days tomorrow. Okay, we good? There's more cookies up here, there's more Capri Sun. Help yourself.